Hello all, welcome to video 1 for section 4.4, coordinate systems. So let's consider the standard basis of R3, and we'll call this basis B, and it's just 1, 0, 0, 0, 1, 0, 0, 0, 1. For each vector x in R3, we can rewrite x as some scalar x1 times 1, 0, 0 plus our scalar x2 times 0, 1, 0 plus our scalar x3 times 0, 0, 1. And the idea is just that these weights that we pick off x1, x2, x3, those are the coordinates of x, right? If we sum these all together, you're going to get x1, x2, x3. And so the basis is really this choice of basis that is giving us the coordinates. Yeah, gives us a way of assigning an address to each vector in R3. And this assignment of, arrow right here means these numbers give you or these numbers tell you which arrow to pluck out. That assignment is called a coordinate system. So let's do a quick example. So here's one from life, more than it is out of mathematics, but it's a good example, I think, illustrating what we're talking about. So length is a vector space. Right? You can add lengths, you can scale them by real numbers. All the things we want from our definition are true. But depending on what basis you pick, the numbers mean different things. Yeah. So depending on what basis you pick, or on the basis, yeah, different lengths mean different things. Oops. Maybe receive different addresses or receive different numbers to represent their length. Receive. Did I get that backwards again? Is it IE? No, that also looks wrong. What did I write down? We'll say get. Why sweat over it? Different things get assigned different numeric values. Okay. So for example, if your basis is 1 centimeter, then you're like 180 centimeters tall. Yeah, so if your basis for length is 1 centimeter, then the numerical value of your height, say, is different from if your basis is 1 inch. Okay. And maybe you've got a preferred basis in the United States. At least people prefer inches to centimeters, but you may want at some point to change bases. Okay. It's supposed to be a 1 there. Let's state this theorem quick. Boom. Our unique, theorem 4.7, our unique representation theorem, which says given a basis B, which is B1, B2 up through Bn, a basis for our vector space V, then for each vector V and V, there is a unique set of scalars. We're calling them C1, C2 up through Cn, with the property that our vector V is equal to C1, B1 plus C2, B2 plus all the way up to Cn, Bn. So in other words, not just that we can have scalars that do this, but there's only one set of vectors that makes this work. And these are going to be the coordinates of V with respect to this basis B. Oops, I put X here, but I meant V. Yeah, these scalars Ci become the coordinates of V. Oops, little v is a vector, relative to this basis. And we write we write that the coordinates of v relative to b basis are these scalars in this order. Okay, so let's do an example. If we take x to be the vector -3, 3 in R2, and instead of using the regular basis, we use this new basis, 1, 1, and -2, 1. And you can check this as a basis. We want to know what is, what are the coordinates of x relative to b. So yeah, what we want to find C1 and C2 so that that x is equal to C1 B1 plus C2 B2. So we know what x is. X is -3, 3. We don't know what C1 is. We know that B1 is 1, 1. We know, we don't know what C2 is, but we know that B2 is -2, 1. Okay. Okay, and once again, this is a situation where we've introduced some new notations, some new ideas, but everything, again, boils down to solving a linear system. Okay, right? We're solving what, 1, 1, -2, 1, C1, C2 is equal to -3, 3. So we're going to take the augmented matrix 1, -2, -3, 1, 1, 3, and reduce this. I'll let you all sort out the details, but it'll reduce to 1, 0, 1, 0, 1, 2, which is telling us C1 is equal to 1 and C2 is equal to 2. And so what? So the coordinates of x relative to our new basis is just 1, 2, and this means that x is equal to one copy of the vector 1, 1 plus 2 copies of the vector -2, 1. Okay, not so bad. I mean, of course, I would say that I've got a PhD in math. Moving on, though, coordinates in Rn. If we let B be a basis of Rn, B being equal to B1, B2 up through Bn, we might want to know, how do we find coordinates for x and Rn relative to this basis? Okay, as we saw before, this just amounts to, solving for the scalars C1 through Cn here. That amounts to, we can put all of these basis vectors into a matrix, and so hitting this matrix with this vector, and we should give this matrix a name. Let's call this whole thing P B, and actually we know what these scalars are called. This is what we've been calling the coordinates of x relative to C, or relative to B at least. Right, and then, oops, this is where PB is equal to the matrix built out of P1, or B1, B2 through Bn. Yeah, and this is the matrix. Matrix that does what? It transforms the coordinates of x relative to B into its original regular standard coordinates. So this is the matrix that transforms coordinates of x relative to B into standard coordinates. Okay, right, and we call this matrix PB the change of coordinates matrix from B to the standard basis of Rn. Right, and you can, since B is a basis, we know that the columns of PB are linearly independent, and so by the invertible matrix theorem, we get that PB is invertible. So in particular, since x is equal to this invertible matrix times our coordinates of x relative to b. This gives us that we can apply the inverse matrix to both sides. So PB inverse x is now equal to PB inverse PB x relative to b, and that's just equal to x relative to b. Oops. And so we get, if you wanted to find the coordinates of x relative to b, one thing you could do was compute the inverse to the change of coordinates matrix and then hit that with the vector x, right? We're just solving this way. Yeah, so the conclusion is, so what our P inverse, our inverse to our change of coordinate matrix transforms standard coordinates into our P coordinates. Okay, and I used to have a hard time. There it is with it swearing. I used to have a hard time remembering which way PB went. And the really helpful thing for me to understand was these three equations. I could tell you that what we want is to write x as some linear combination of the basis vectors. And what I needed to remember and couldn't as a student was that we've got this like very natural matrix popping out and this very natural vector popping out. And that natural matrix is our PB. And this vector that we've seen before is our coordinates of x relative to b. Okay, hope that's helpful. I'll see y'all next time for part 2. Take care, everybody.